Hello everyone. Today I will be presenting our work on improving serverless application workflow security. This is a joint work in collaboration with University of Illinois at Urbana-Champaign, Stony Brook University, Samsung and Silicon Valley Bank. First, I will explain a little bit about serverless computing or function as a service cloud. Serverless cloud is the newest paradigm in the cloud computing domain. It is just another layer of abstraction to free the tenants from the burden of cloud infrastructure management tasks, like load balancing and scaling, for example. In serverless computing, tenants only need to implement an application's logic as an interdependent set of functions, each of which will perform a specific task. To achieve the operational goals of the applications, these functions coordinate through interaction with other components like event triggers, message queues, and object stores. The serverless cloud has become highly popular in industry due to the reduced management time and cost. Such platforms will automatically scale out function instances to respond to highly variable request load. Moreover, the pay-per-use model allows tenants to only pay for the computing cycles the function executes for. Also, serverless ecosystem enables rapid prototyping of applications, allowing tenants to use purpose-built functions from public markets or license-based functions or third-party dependencies in their custom function code. Consequently, the serverless market's growth is expected to exceed $8 billion per year by 2021. Although all this sounds very good, there are some pitfalls as well. The diverse and distributed nature of serverless applications has led to the resurgence of prevalent cloud security issues like cross-tenant side channels and other web application vulnerabilities. Consequently, the attackers are now equipped with an arsenal, no, not the soccer club, but set of attacks against existing cloud security measures directed towards numerous heterogeneous components of the serverless ecosystem. What makes things worse is that a recent study claims 21% of 1000 open source serverless projects already contain critical vulnerabilities. However, serverless functions are ephemeral and stateless. They will only run maybe for a few cycles and then the instance is destroyed. Cloud providers argue that the vulnerabilities are difficult to exploit in practice, and serverless is in fact more secure due to this ephemeral nature of functions. Is this claim really true? Let us find out the answer to this question through a case study of a real estate website that has transitioned to using a serverless cloud backend. This has already been done by popular companies including Realtor and Zillow. The website clients in this case are the real estate companies who post property listings on the website. And here we show an exemplar serverless architecture for such a website based on several case studies made available by Amazon AWS Lambda on their website. The real estate companies can post listings or upload their customer base information or some other important documents through exposed APIs in the API gateway. We will look at one example flow in this serverless application. Function F1 is used to upload the client and customer information, and this information is uploaded to a database D1, and function F2 can add a verified label to some specific property listings after consulting the database D1. The white box for F1 denotes that the application developer wrote this function by themselves, whereas grayed out function F2 is a third party function and thus they may be closed source or their behavior could be unknown. Next, function F3 can post the property listing to the website and triggers function F4 to advertise the listing through several channels. F4 in turn invoked F5, which is a messenger chatbot function to advertise the listings to customers through some messenger application. Now, F5 is allowed unrestricted access to the internet for its operational requirements. Also note that while the application developer writes function F1 and F3 by themselves, F2, F4 and F5 all are third-party functions. The workflow developer configured the Identity and Access Management or IAM rules and static function specific network policies to restrict outbound internet access to all functions except for those who strictly needs it. In this case, none of the functions are able to access the internet except for F5. Now, in this setting, what new problems can occur due to unique serverless features? Recall that ideally serverless functions should be stateless. However, to improve performance, cloud providers do not spin up a brand new container every time a function is invoked. Instead, they employ container reuse policy, which means that the container hosting a function is cached in memory for some time period, and function requests are routed to a pool of warm containers. So, in this scenario, what problems can occur? The untrusted function F2, because it is a third party function, it can have an exploitable vulnerability. But the attacker cannot maintain persistent control of the function because it is ephemeral. Instead, what they do is that they write their malware toolkits into the temp directory of the functions that they have access to and then abuse the worm container policy to make sure that these toolkits remain in memory as they plan their attack. Next, as the attacker observes transactions from database D1 to function F2, they can steal this data and now they need a way to exfiltrate. But recall that F2 does not have direct access to the internet. Instead, attackers can make use of legitimate API calls to launder the data out to a location under their control if possible. Now, how is this possible? For example, they have the messenger chatbot and they can send the customer credentials to their own messaging account through that messenger chatbot function, which is F5. So, this way they can bypass the static network policy and exfiltrate information through valid API calls using downstream functions. So the data will travel from F2 to F3 to F4 and F5 and then finally to open internet. These attacks demonstrate that in spite of serverless providers' claims that serverless is innately more secure, the existences of these tactics create significant rewards for attacking serverless applications. The previous examples provide us with a key insight, which is the common pattern in such attacks are the untrusted third-party functions who may introduce unintended flows within a serverless application. So, the obvious solution to this problem is we need to detect the violations of intended information flows in the application and prevent the occurrence of these violations. Now, can existing solutions be used to combat these threats? We will look at two types of solutions. Firstly, the pre-deployment tools. These include language runtime libraries that secure a single function according to developer defined policies as part of the source code. Some of these solutions employ static analysis of function source code and configuration files to detect violations of the principle of least privilege and checks function dependencies against vulnerability databases. However, these solutions are largely function centric and their efficacy depends on the correctness of the policies written by the function developers. And it also needs complete access to the source code. Moreover, most of the times this work only with specific language runtimes. So such pre-deployment security tools will be unable to transparently discover implicit flows among different functions in an application. Another type of solutions employ runtime protection mechanisms. One of these are machine learning based detection of anomalous function behaviors. But the success of this solution will depend on the robustness of the machine learning models. Another approach attempts to prevent event data injection by inspecting incoming function invocation requests using existing pen test techniques. The completeness of code injection analysis determines the usefulness of such solution. Another variation of runtime solutions focus on providing better observability into serverless applications. These are usually execution tracing techniques, error reporting, alerts, and monitored metrics of function executions, and these mechanisms are provided by the serverless platform itself most of the time. However, existing monitoring techniques offer limited observability into the interactions between functions, and most of these monitoring services are limited by strict usage limits. There are some third party observability tools that offer more features like distributed tracing and cost analysis, but they are limited to certain language runtimes and platforms. Finally, most of these solutions are mostly geared towards function level protection and do not consider more complex information flow violations. So, they cannot provide a holistic view of the application, and we are not aware of any approach that considers the matter of container use tactics. So that is why these solutions are unable to prevent the attacks we have discussed before. So we present our system valve to prevent the explained attacks. The main idea is to mediate information flow across multiple functions and multiple invocations of the same function through monitoring how the functions are interacting with other functions and the internet. The system consists of two components. One valve controller that runs as a service within the serverless cloud platform, and a valve agent that is part of every function instance or container. We will use the term function instance and container interchangeably. The goals of our system are that we want our system to be transparent to the serverless functions so that no modification or instrumentation is necessary to the functions. Valves should also offer us a closer look to the interactions within a serverless application as a whole and should provide fine-grained observability. We want to dynamically monitor the function instances constituting a serverless application and enforce a flow control policy to only allow intended flows. And lastly, valves should also be widely applicable to current serverless platforms as a plugin or with minor modifications. Next, I will go through the architecture of Valve. So, the serverless functions are executed inside containers. The Valve agent also sits inside the function container and performs several important tasks. The first component of Valve agent is the garbage collector. This garbage collector essentially deploys a system called tracing mechanism for monitoring function file IO. The tracer intercepts and records all system calls issued by the function using the strace utility. For file operations, the tracer records the accessed file, offset, and bytes accessed. After the function finishes execution, all data on disk that was modified by the function is erased from the container. And currently, container reuse attacks this require an explicit data flow from one function execution to another. So garbage collector is sufficient to deny cross invocation capabilities to the attacker. It also provides fine-grained observability in terms of file access behavior of the function. The second component is a network proxy which performs API monitoring of a function. The event-driven nature of serverless enables functions to heavily depend on web and API design paradigms, and most of the interactions take place in form of REST-based API calls. To observe API usage, Valve deploys a transparent forward proxy in each container that begins proxying network requests when the container starts running. This network proxy fills all incoming and outgoing network requests originating from the container. Thus, the network proxy serves as a transparent mediation point that allows us to observe the dynamic behavior of functions while avoiding dependence on source code, instrumentation, or assumptions of language. Next, the network proxy passes this information to the taint propagator. This component determines taint labels with timestamp, flow ID, and REST API information for the current flow. Next, a message broker and the Valve controller service comes into the picture. The Valve controller runs as a service in the FAS platform and coordinates among the different application components to manage the application workflow. The generated tent by the tent propagator is sent to the tent auditor of the Valve controller. The tent auditor records all these tents in a centralized log and additionally propagates the cumulative tent for the current workflow to downstream functions. As a result, each flow in the application accumulates tents as it progresses through the workflow. The policy generator in the Valve controller looks at this taint log and produces an allow rule for every flow observed by the taint auditor. During this application profile phase, the default whitelist policy is presented to the workflow developer. This default policy not only serves as a starting point for iterative policy refinement but also simplifies flow policy writing greatly for the developers. After the default policy is derived, Valve can be switched into enforcement mode. Request validator within the Valve agent is a policy enforcement point. The API request validators within the Valve agents will begin to deny accesses that do not adhere to the function rule set. When a function invocation request is received in the container, the request validator extracts the tent level from the inbound request and references the policy to determine if the request is authorized. Then it can either allow or deny to forward the request to the functions. The enforcement is transparent to the function. Now let's talk about how our system was implemented and evaluated. We implemented Valve using programming language Go on top of OpenFaaS, which is an open source serverless computing platform. We have minimally modified the OpenFaaS source code to instrument the request handler in each container to proxy network requests and track system calls as part of the Valve agent. This demonstrates that the principles of Valve can be easily incorporated into existing systems, making it widely applicable. To prove the generality of our results, we ran each experiment against several different corpora of serverless applications. The first one is Hello Retail, which is an event driven AWS serverless proof of concept retail application from Nordstrom that leverages AWS services like Lambda, Kinesis, Dynamo, and S3. We also use 8 model functions from OpenFaaS function store in our evaluation. And finally, since we envision that trigger action platforms will move to serverless setting due to their support for event triggers and actions, we implemented 2 proof of concept workflows based on trigger action rules. First, I will talk about the build costs. The build costs in Valve are one time and primarily incurred by the cloud provider while building the container images for different functions. The average increase in image size and build time are respectively 97% and 51%. However, we can improve these costs in two ways. The primary source of these overheads is caused by adding MITM proxy network proxy to the container image. This is because MITM proxy is a mature and trusted software artifact that is considerably more feature rich than what is strictly needed by our Valve implementation. And finally, Valve's design is independent of the proxy used, and we can use any lightweight alternative of MITM proxy. We can also use container debloating techniques to reduce the image sizes. Now, large image size is a long-standing research problem in container ecosystem, and it's orthogonal to the goals of Valve. The runtime costs are more important metrics while evaluating a system. However, for brevity, I will only discuss the Hello Retail test suite performance overheads, and further details are available in the paper. We compare the performance of Valve against two baselines, a standard vanilla OpenFaaS deployment and a language-based information flow control mechanism called Trapeze. In the left, we see the function deployment time for different functions, which is the time taken to deploy a function for the first time to a serverless cloud. And in the right, function teardown time is plotted, which is the time taken to remove an active function completely from the cloud. Now we observe performance characteristics similar for both the system Trapeze and Valve, with Valve imposing a fairly constant overhead of 6.5%. However, the most critical performance cost is the function invocation time, and it also shows modest overheads for Valve. This time is the round trip time starting from the invocation of a request to the receipt of the response. The average overhead of Valve in this case is just 2.8% per invocation. Valve exhibits fairly constant runtime overhead compared to Trapeze, where overhead varies depending on the function internals as shown in the figure. This is because to achieve transparency, Valve's flow control model is intentionally coarse-grained and lightweight, and Trapeze, which is more heavyweight, it offers flow control at the memory level while being more intrusive and expensive. To conclude, I presented our flow control system Valve, a generic and transparent serverless dynamic flow control architecture with modest runtime overhead. Our system offers fine grained observability into a serverless application and helps developers to design secure applications. Our system code is open source and is available at the given link. Thank you for giving me this opportunity to present our research, and I am now open for taking any question you may have.